Okay, so welcome to the second week of our course. My program today will be to represent L1 as a subspace of the bounded measures. You know, it was my kind of trick to say, why are we studying convolution? Not because it's so mathematically challenging, but because it appears very naturally in the engineering courses when they talk about linear translation invariant systems. And there you have to choose a model, and the mathematicians choose some domain and some target space. And the more or less, for me, the most simple object among all the function spaces is certainly the functions which are continuous, complex valued, and bounded. And within that space, the closure of the test functions for now means compactly supported continuous functions, is maybe the easiest space. So this is what we call C0, the space of continuous functions vanishing at infinity. So we have Bibos systems which map bounded functions into bounded functions, decaying functions into decaying functions, and we can even control the size, the maximum of the input, by the maximum of the output. So normally you derive a system by having some input which is energy or so, and that's kind of limited, and you hope that of course there is no explosion going on by accumulation of energy on the outside. So in that sense, personally I think it's a relatively realistic system. Now, because of the translation invariance, you can show that every of these systems is a moving average. So if you understand what happens when you map a function to the value of the function at 0, and that's a continuous linear mapping, then you know what you have to do, and then you move it around, and it's a moving average with constant profile. Now, in order to be consistent with standard terminology, we have to flip this moving average envelope, so to say, and describe it as a convolution kernel, which has the side advantage that if we take very simple linear functionals like a delta, we pick the function 2 values to the right. Means we're moving information backwards, so delta 2 would, moving average viewpoint, move information to the other side. Therefore, we have this flip operator. So that's how we can do it. And before going into this, I wanted to show you a little bit some features of GeoGebra or so. I was doing various things with MATLAB in the other part, in the practical part of the course, but certain things I prefer nowadays to visualize with GeoGebra. And because it's free, because it's high quality and very flexible, and especially allowing dynamic representations of things, we had, of course, this already running. So what is the function that you get by convolving a triangular function with a triangular function? Very quickly, on the left-hand side, you see the input. So the most complicated term is how can I get the blue function? And I was because there was not a maximum of 0 and 1 minus x command, I was doing it by hand as I was remembering from my courses. This is the blue D or M course. So maximum of 0 and triangular function, so to say. Once you have the blue function, it's really just writing the D row operator to say I can stretch it. So I get the red function. And what you see is the convolution between the red function and the green function. What you have to do is take the green function, flip it around. Well, it's symmetric, there's no problem. And then you do pointwise multiplication, and then you integrate. What you see here is the area of the pointwise product. What you also see, it has a funny shape in the middle. So you will see some piecewise, this is a parabola or so, and so suddenly it splits into two things. If you do these integrals, you would probably split and have cases, case number 1, 2, 3. Here you can see where the truncation points is, or so it's really nice. So actually, I was doing that kind of computation as a PhD student, and I gave up because I thought to do the B-spline of order 4 or higher would be too cumbersome. Now we could go on. You see here only, if you go into the code, it's really doing integration. So it's by kind of obviously, I would say, a relatively cheap integration rule because it looks not perfect. So I think I would have to learn more about how the Riemannian sums built in this routine. But it should be fast, so I want to go from point to point. At each point, really, I plot the shift parameter. You see it's moving dynamically around. The shift parameter b against the height of the point, which is the integral, is the yellow area. So this is not exactly the ordinary cubic spline, but something quite similar. And you can, of course, think, what is the Fourier transform of these functions? And I was playing around with this. I don't want to do it now. But it's clear that if you have sinc square is the Fourier transform of a triangular function, you take the product of two sinc squares. And then I observed it's quite nice to play around with the dilation parameter and to see when are the side lobes minimal. So and that was the choice of why I choose the red one as opposed to the blue one, because I found that is a little bit more beautiful. So I'm getting a kind of more smooth things, which is really, I mean, at very first sight, is closer to the Gauss function than the ordinary cubic B-spline, which you get by taking the forced convolution power of one fixed rectangular function. Of course, you can play around and take convolution products of many rectangular functions. Each of them increases the smoothness. So if you need a C20 function, take 20 rectangles. If you need to restrict the support size, make them smaller and smaller. Of course, the derivatives will increase, but they have so and so many different derivatives. So that was one thing that I wanted to show to you. Another thing is I was explaining to you in the MATLAB viewpoint.
Looking very nice.
Yeah. No, I think the main point is that you can give this, I mean, you can play around yourself and you can give this to your students and they will start playing with it. And they will ask questions that they would never look if you would put them as assignments. So I think it's a very good thing. Now this, I'm not sure if I look at the left-hand side, I'm relatively sure that this was done by one of the people doing internship with me some years ago. And I'm just now in contact with some of these people and telling me that they are now at the Technical University in Vienna and they like to do mathematics because they learn to play around with mathematics and get interest in it. Now, again, you can say we all know what Lagrange interpolators are. So if you have the function values of some function, and these are given by these points, then you can put the number of points and have a polynomial of the given degree. If you spell it out, it's of course some work to do. But the good thing is here, you can take these points now and you can move them flexible. They are even, I think these are just, yeah, you can even move them in this position. So you can ask, what is the resulting curve with so and so many points? That's of course the order of the polynomial, and get a very good intuition what it is. I mean, if you start with, I don't know, 4 points, then you look at more or less at all possible cubic polynomials. And people will very easily realize that they are something with a jump. They go to infinity in opposite directions. Maybe they start here, but then they will end in the opposite direction. What is the reason? Well, you can somewhere look at the coefficients of the polynomial. So it's really a good playground. So I wanted to tell this to you because the relation to our course is, of course, that I was telling you that the Fourier matrix, so the matrix describing the linear mapping FFT, input is a column vector, output is the FFT of this, or the DFT, coded in a fast way, is the same as the Vandermonde matrix, which maps coefficients of a polynomial to the values on the unit roots of order n, taken in mathematical clockwise sense, because we are going opposite to the mathematical sense. We're going downwards, starting at 1. So if somebody is giving you 8 points, you have unit roots of order 8, starting at 0 degree, minus 45, minus 90, and so on. You have 8 points, giving you an 8 by 8 Vandermonde matrix, and you can easily understand that this is has something to do with this. The inverse of it is then, of course, the matrix telling you if I have the values of the polynomial, I can get back to the coefficients. And this, we will discuss later on, is really the basis for the convolution theorem, because convolution is what you do when you multiply numbers, when you multiply polynomials. And if somebody tells you, I have multiplied the values of a polynomial and so many unit roots, then of course you know that the product of two polynomials will have the pointwise product of the values of a polynomial. So I mean, nothing magic. And if somebody tells you, well, but if you tell me the values of a product polynomial on so and so many unit roots, I can compute what the polynomial is, then you have an easy way to compute the Cauchy product or to multiply out. And just imagine that somebody tells you, please take the square of a natural number with 500 digits. you would say, oh, that's terrible, you cannot do it. I mean, it was even a punishment for students. Maybe you had the same tradition of students who were kind of making noise in classroom. I don't know, before I was going to school. I was not suffering from it, but maybe the generation before me. And so it was called Zapfen in German, but it means, yeah, well, you have to write something and then you have to write through, so very likely you have some errors, so you're frustrated, and that's your punishment. And that's how you make people feel bad about mathematics. And I mention it because when I was a young assistant, this is a joke now, but it's a true story. There was a father coming up to me, I mean some father from a student at high school, and asking me as a young assistant, I mean, my son is getting this stupid assignment, isn't there any computer program to do it? And I told him probably there was a good reason why the teacher was doing it, but let me think. No, I don't know. I don't know. Maybe somebody can program it. The numerical analysis people might know it, but I would think maybe some up to 20 or 50 digits at that time or so. Nowadays, I will mention this later, I can do it with MATLAB. I can take the cube of a polynomial, I mean of a number with 2,000 digits and so on. It's a long string or so, but I can do it because I can convolve signals. Signal analysis people are, of course, taking, I don't know, FFT of a signal of 100 microseconds. 100 microseconds is 1/10 of a second. If 1 second is giving 44,100 samples, then of course 100 microseconds is 4,410 samples. FFT of that size, no problem. You can even do it continuously, kind of moving your window over your signal. So in that sense, we can do this kind of multiplication, and they're closely related. I have already talked too much about these things, but I would like to mention another thing, which again was something I personally must say I've learned from MATLAB, using MATLAB, or learned from using GeoGebra, various things. The most important thing I've learned from MATLAB was there is a command called PINF, which is the pseudo-inverse, which is the Moore-Penrose inverse, which is kind of the mathematical way of expressing the the minimal norm least square solution. And nowadays I'm teaching this as one of the most important consequences of linear algebra. Through the singular value decompositions, you can get the PINF, and from there you can understand frame theory, respaces, many other things. And if you know what you can do in linear algebra, you can do it in MATLAB, you can do it in Hilbert spaces, and then you can generalize from that. So that's one of the reasons. So one of the concepts that you learn in abstract Hilbert space theory, or even in linear algebra, is for every basis there is a bi-orthogonal basis. So somehow the key idea is somehow is giving you few vectors. I can only take 2 vectors in this here, in a higher dimensional space, and you would like to have an orthogonal, I mean a description of the orthogonal projection of a vector, which may be outside or inside, onto this plane. So somehow you would ask, what are the coefficients of the normal projection or so? And the natural idea might be you should do first Gram-Schmidt, so you orthogonalize it. But if I see these 2 vectors, which one is the first one and which one is the second one? People sitting here might say, for them, this is the closer one, this is number 1. And so already Gram-Schmidt is depending on the enumeration, and we can discuss this separately. But somehow I thought, well, if we have a 2x2 matrix, and that would be these 2 points on the unit circle, then I would like to demonstrate if you put these 2 vectors in R2 into a 2x2 matrix, then we all know if somebody wants to represent a vector in this coordinate system, you have to know the inverse matrix. Now, because we don't like to write matrix multiplication with inverse matrix multiplication, but we would rather say matrix multiplication and the other matrix with transpose conjugate, because then we can say what we are doing is exactly what we do with an orthonormal basis. We take the coefficients, but now with the bi-orthogonal system that tells you what are the exact and uniquely determined coefficients, and then you synthesize. So kind of how can you find out the first coordinate of the projection and the second coordinate in my simple-minded example. In the general situation, if somebody is giving you in a huge Hilbert space finitely many vectors, in general position, how could you compute the orthogonal projection? And roughly speaking is, well, you have to correlate your vector with your original and try to find the biorthogonal system from this. Okay, so I thought, okay, maybe just to show the students how they can get, using GeoGebra now, if I put two random vectors and I put them into a matrix, it's a bit cumbersome here to generate the matrix, but 2 by 2 matrices are easily invertible, so how can you illustrate it? Now, then I realized it's not very nice if you move things around. It's much better if you take unit vectors. So kind of the matrix is a little bit balanced, and you all know if you have two vectors which are not of length 1, you can multiply with a diagonal matrix to resize them. So to assume that the matrix has column vectors of length 1 is really not a difficult thing. Now here comes a very good feature with GeoGebra. So later on in the practicum we can really kind of try to do this within, I don't know, the key part of this within 3 minutes or 5 minutes, if kind of with some exercise. What are you doing? You're saying, I need the center. Then I need, at the center, a circle with radius 1. Then I click twice and I have 2 points. And then I have the vectors from 0 to those points. So once I have 3 points, I have already 2 vectors. Then some typing tells you, well, write this into a matrix, compute the inverse matrix, and then I was visualizing. Now, these things can be moved on the object. So somehow what you can do is you can move these things. So, and the red arrows are now the entries of the biorthogonal system. So we should say that's the rows of the inverse matrix. So I can, and I claim now from this interpretation, I can even construct the row vectors of a 2 by 2 inverse matrix. Now, what you see without big understanding or philosophical considerations is now is a situation where the angle between the vectors is acute. So between A and B, the vectors u and v, they have an acute angle. What is the property of the biorthogonal system? They are, of course, in an obtuse angle, so they're open. I can change the situation, and it's, of course, a symmetric situation. I can make that white. Now the black arrows are white, obtuse angle, and the thing. So now you can guess when is a system self-biorthogonal. And that's, of course, the definition of orthogonality. It's exactly when you have the transition between this, and that's now, this is perfect. Here the inverse, the rows of the inverse are the columns of the original matrix. And if you write it in complex terminology, you have to put the conjugate or so. So a priori, I mean, we are already used as if you're a trained mathematician, that orthogonality, it's a very nice concept, and that's so good. And you even learn that you don't need to invert the matrix to do it. You just take the coefficients or so. But somehow it's some kind of, you don't ask again, why is it? If you see these pictures, I found it, for me, it was improving my understanding of orthogonality. And then now the other thing is, what is this construction? I mean, I was kind of first, let me say, maybe take this situation. I was first illustrating it, then I was making an observation, and this one was really done based on the observation and interpretation. How can I construct, let's say, the red vector B2? This is the first vector, the second vector, and the B2 is the biorthogonal element to the second vector, which is the U1, this vector. Clearly, you have this vector here, and you have to take a perpendicular. Again, click perpendicular vector to this, and you have the line. Then intersect, no, then have the tangent, the green line. Well, clearly the tangent is moving from this, going through this point perpendicular to this. Click, 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 and you have the tangent. Then I'm intersecting the green tangent with this directional line going through this, through orthogonality. And this point, what I call D in this picture, this is the end point of this. Why is it like this? Well, the biorthogonal system has to have the property, it has to be perpendicular to all the other ones. So B2 has perpendicular to B1, so that's why it's having the direction. And the projection has to be 1. And that's now where you see the triangle. You have this nice triangle, rectangle angle because of a tangent, and the orthogonal projection of B2 on the other one is exactly 1. And that's because, I mean, this is a radius from the unit circle, so the orthogonal projection happens to be 1, and because these are points on the unit circle, this interpretation is quite nice. So in this way, I really start, the construction works and is dynamically arranged on the basis, if I move the points, the tangent are moving with the points due to GeoGebra properties. The orthogonal line is also moving, therefore the intersection point is moving, and I just have to color everything and display it, and you understand very good why orthogonality in the sense of 90 degrees so good is in a geometric sense quite obvious. And so again, inverting a matrix is equivalent up to this transpose conjugate to find the coefficients from the linear combination. And if you are in a situation where you don't have a square matrix, but you have a matrix of maximal rank, then the first point is, again, you have few vectors in a high-dimensional space. You have to invert the Gram matrix. But if you are having a maximal rank in the other direction, think always of, I have now 5 vectors in R3. They're frame of redundancy 5/3, the generating system. So you have to make the 3×3 matrix that you get by first taking the coefficients, then inverting it, and then you get 5 vectors again, and that's the dual frame. We will discuss this in detail, but just to mention it. Okay, I think that's more than enough for this, and we will go back to our slides, and I will, but maybe if you have short questions, I can treat these questions. Yeah. Maybe I think I have not explained this too much. So are there questions concerning these GeoGebra things? Of course, I can privately discuss details. And I have many, I have quite a few more. And if you're interested, I can give you details. And I've uploaded to the web page maybe something like 10 now that are illustrating more. I was choosing these 3 because they are most interesting from my point of view. Okay, I have decided, and that's maybe a side effect of this course, that I'm now trying to teach you how to use MATLAB, and I know essentially how to do relatively quickly illustrations of what we are discussing in a theoretical setting using MATLAB. So in the practical part, we can even discuss details how to do it. But I show you essentially how I would nowadays illustrate what we have been doing so far. So we have discussed moving averages are coming from abstract functionals, which are called measures, because it's justified by the Riesz representation theorem. And we have seen that the measures are not, the discrete measures are the easiest objects. You can take linear combination, point evaluations, Diracs at different points, as point evaluations are a simple definition, finite linear combinations, limits of finite limits, which turn out to be just absolutely convergent sums. I don't discuss this part in detail, but it's clear you cannot reach everything if you are stuck with the norm topology. So you have to do something more general, and that was the weak star topology. So the question is, how can you approximate a measure by a discrete measure? And somehow the idea is, I think a probabilistic viewpoint is quite good. I'm saying, well, I have created here a probability distribution. Actually, I was computing a low-pass signal, so I was taking random Fourier coefficients, throwing away the imaginary part, multiplying with the plateau function to have something which is concentrated, and so it's non-negative, concentrated, so that the total sum of all these samples is 1. So somehow I'm thinking of a continuous, also it's of course just a vector in 480-dimensional space. It's ending here. And then I said, well, a rather coarse partition of unity would tell me what the discretization is. So you can think, roughly speaking, if this was a collection of rectangular function, I would tell you that please take a histogram and take as amplitude of the Dirac at the midpoint of the bar, so to say, the height of the bar. That's, so to say, the idea. But we are dealing with functionals, so how can you deal with functionals? Well, you have to let these partitions of unity act on ordinary function. So that's maybe a too crowded picture, but I was trying to tell you we had the operator spline approximation. So spline approximation says I'm taking samples, I mean one sample equidistant in our case at each member of the partition of unity, and that's the amplitude for something like this. So piecewise, I mean rectangular function would be step function by sampling. People would call it sample and hold, for example. If you take the first value of the coordinate, wait for an interval, next value, keep it. Nearest, I mean, or you get the midpoints. So more or less the graphs that you do when you do Riemannian sums. Or MATLAB is doing piecewise linear interpolation. It connects, and I say, no, you are summing up triangular functions, but that's the same. And here I was doing the concrete poo-poo that I was showing to you. And now you have, unfortunately, 4 functions, real valued, imaginary part, and you can guess that, for example, I think the red and the blue one are the original ones, and then the other colors are the corresponding spline function. So you see this peak or so is cut off or so. So it's a relative, I mean, actually I would say it's, I wouldn't like this approximation, it's too coarse, but it's telling you somehow these functions, these are the point evaluations. So I think the blue ones are the point evaluations of the real part, the red ones of the imaginary part. So somehow, of course, the interpolating curve, or the, not the interpolating, the quasi-interpolating curve is following it. If the curve was very smooth, you would just see maybe it's a little bit like a smooth step function or so. But if I would make the poo-poo finer and finer, you could see how it is increasing. I have not the GeoGebra version where I would say the parameter is the width of the triangular function, and you see how it melts towards the continuous limit. Now, but taking this, so it's not so perfect, but taking this, I can pick up, and that would be a kind of rough visualization of what you get by this kind of smooth histogram. So I was saying, for each value, I apply my measure against this poo-poo. What I did, of course, I just did this color product of my signal, discrete signal describing this density distribution against this family of vectors describing the partition of unity. So it's just the ordinary scalar product, but in general things it's applying a measure to a function. So I get certain values. Now these values, of course, turn out to be at a different scale. So what I was just doing for visualization is I was doing the maximum of these red dots, because these are really Diracs. And like engineers like to represent Diracs, I was doing this needle type of representation. So you pin a needle, and the head of the needle is the height of the amplitude of the Dirac. So just to show you, it's following the graph, but definitely because, I mean, a measure would not have values. For example, I could take a delta, and I could try to see what happens if I take this delta or this delta or this delta and do all these things. Then maybe if I'm in the region overlapping where two parts of the partition of unity are overlapping, I would see still some diffuse discrete representation. So I would not get back a discrete measure, because I have to put all the information into a grid. What's clear, if I make the lattice finer and finer, this situation will improve. Now, the main point is actually the second part. Yeah? Oh, thank you. Thank you. The main part is to tell you what you can see in the distribution function. So the blue curve in the middle is the distribution function of the continuous density that you see upstairs. Whereas this is something which has the height, the jumps are distributed according to these laws. So it's again going from, so to say, from 1 to 100% or so. They're at the location that you have here. And you see there are big jumps and flat jumps. So this is a small amplitude, that's a little jump here. There are larger jumps. I think one could play around to have something where it's more significant. Maybe you have some really big values and some small values. But if you look closer, you see this is distributed, and actually you could choose these points in a different way. Your partition of unity could be in not a regular one, but maybe small triangles with short sampling or so. Then you would see the mass distribution is important. It's not the amplitude of the deltas. So very much like a Riemannian sum. Somebody tells you, I have a Riemannian sum with 10 sampling points in the unit interval. Then you have some amplitude. Then you say, I have a refinement. I have now 40 points. Then the amplitudes would go down. You would say, well, he has done a finer step functions. The total height is, of course, the same, but the steps are smaller and finer. And in the limit, it's the continuous thing if it's a continuous distribution. So my interpretation, which I think is reasonably well justified, but I cannot give you a historical argument or so, is that people in the early days were looking at these distribution functions. They were talking about Fourier-Stieltjes integrals, so they were really using, instead of the measure, they were using the f. So they were saying a Riemann-Stieltjes sum for a given measure, so integrate something against this measure, would be f of xi, but then instead of saying the interval length is xi plus 1 minus xi, it would say it's the height of xi minus 1 minus height of xi. So as I told you in my story with the biker would say it's just, I don't know, half a kilometer, but it was so steep, therefore the f was very steep, and it was costing a lot of work here. The other part was fairly flat, even if it was a short, if a long piece, the difference of values would not count as much. So you have a variable length. And so they were saying, well, I have certain things that are going, these measures are convergent. So they would not look at the measures. They have no concept of measures, maybe 120 years ago or so. They would look at this distribution function and see how they approximate these things. Now, a very good example is we could take, which we know is convergent to the Dirac delta. Dirac delta corresponds to a jump function. Now, I'm a little bit vague in my statements, but I think you can follow me. And I can say that Gauss functions compressed converge to it. So what would be the shape? We could also do an example in MATLAB. What are the Gauss functions? Well, this would be steeper and steeper. So you have continuous functions convergent to the step function. Now you can imagine that it depends where you put the value of the step functions. Maybe you say it's left or right continuous. So if you put the value here, then the chance is that at that point where you have a jump, it doesn't converge. And my interpretation of why the word weak came in the whole story was, well, ordinary pointwise convergence, maybe uniform convergence, that's the right concept. Now you're taking something which is a little bit softer, a weaker version. So you're saying if it's convergent at all the points except the points where the limiting function has a jump. And then they were generalizing it, and then they were saying, well, it's measure theory. Now we have Banach spaces or so. And then you have, well, we are living in a dual space. That's why we say it's star. And it's a weak form of convergence. So that's, I think, why the word weak star convergence came in. And so it's not so bad and very important concept. I find it very important. You also have, if you look at functional analysis, weak topology. So that's where you would say a sequence in the Banach space, not in the dual space, but in the Banach space is convergent if every linear function applied to it is convergent. And I have discussed with some colleagues in PDE or asked my students, and they said, well, in our course we have not heard the weak star topology. We only heard about the weak convergence or so. And I was slightly, no, not embarrassed, but I was surprised or so, until I realized, well, these colleagues are in partial differential equations, and whenever they work with other spaces, they try to use Hilbert spaces. And when you have reflexive spaces, and in particular Hilbert spaces, the weak topology and the weak star topology are the same. So my statement, the weak star topology is something that you should keep in mind, or the weak star convergence is extremely useful, is still valid. But if you're not living in the world of general Banach spaces, then it's the same as the weak topology, and you can be happy to work with one of them. I think both of them are useful. In the general case, I will work with continuous functions, measures. These are not reflexive spaces, clearly. You have L1, L infinity is not reflexive. So I think it's more important to use the weak star topology, because something that's not done in all the courses is if you take, that's just for as an outlook or a kind of to the starting point for other things. If you take a dual space, you endow it with a weak star topology, and then you're asked, what are the weak star continuous functionals? Then you're not getting the bidual space as you would get for the weak topology, but you're getting just the original space. So kind of start with a space, go to the dual space. Normally you learn it's a Banach space, it has a dual, and you go on, and non-reflexive spaces you get an infinite chain of spaces. Banach spaces always allow you to put the weak star topology on the dual space, and then you come back. So if you have this trick, then you are almost having reflexive spaces. And why is it useful? Because then many things that you do with finite dimensional space can work. So in Rn it's almost ridiculous to talk about dual spaces. You say column vectors, dual are row vectors. Dual of row vectors are column vectors. Yeah, what's the it's very, very simple or so. If I tell you that the bidual space of cubic polynomials is the space of polynomials, that's already a little bit more abstract, but eventually I'm talking about every four-dimensional space is isomorphic to R4, so I'm just using this, but it's not a natural thing anymore. So I'm going to this other thing. Okay. Let me see what else I have. Yeah, this I will do later. Yeah, just before starting a new section, so to say, I wanted to show one slide of the gaborator, so that's also in the record. So the gaborator, as I mentioned, maybe at some point we can play it or so, is a software, as a website, so you can search for it. It's easy to find now, which was set up only November last year, November 2017, and it's based on a talk and a person who was implementing things which are published in 2 papers by 2 of my former students. So Monica Dörfler already has been a long time with me. She had a cooperation project with Tony Grill, so he's the musical guy in the team. And Nicky Hollighaus was a PhD student with me and then went to the Acoustic Research Institute, so he's quite familiar also with the LTFAT toolbox. And Gino Velasco was visiting Vienna and spent about 4 years. He was coming from Philippines. He went back, so he has an academic position there. And so I think we are all pleased to see that somebody from the audio community was thinking that these splitting of the Fourier transform into frequency bands which are adapted to what audio people would find appropriate. So it's not exactly what the mathematical community is using, dyadic intervals for the description of Beer's spaces, not equal intervals, what we use for Gabo analysis, just to have these buzzwords. And this is a piece of Bach. So you have to think somebody is playing very nicely the piano, and almost you can, no, not almost, you can read the score that he's playing. So of course he is not hitting so many keys at the same, this is the time axis. But when you hit an accord, then of course the overtones will come in, and you see which are the tones that are coming at the same time. And then I must admit, first I was not looking at the left lower corner. Then I thought, well, is he asking for 50 cents shareware contribution? No, no. These are the informations. If you are looking at the most, I mean, probably the most important amplitude, it's describing how many hertz it and how you would describe it in musical terms. So it's really almost transcription. I mean, if you read it out, you can say, well, this was a C, this was a G. So you can try to get back to the accords in the musical notation or so. And I think that's quite remarkable. And one of the things which will help me and maybe you later on to describe time frequency analysis, which is really close to the understanding of signals through musical signals. And when we talk about Gabo multipliers, I can use this picture again. I'm saying the audio engineer would maybe say, this is too loud, these frequencies are too high, so he would multiply it down. But later on he would release his slider and put it back. So if you have a filter, it would be this here. So your favorite filter the old hi-fi devices, you would put your how much bass, how much high frequencies you put, and that would be a multiplication in that direction. But if that's becoming time dependent, suddenly you have really a very nice chapter, and we would say it's a Gabor multiplier. And if somebody is giving you a general operator, can you approximate it by a Gabor multiplier, or which one are the best approximations, and so on. So this is really just an indication of what we will do later on. This is just for the things. Now, the next term or part I have put into these slides is recall the concept of Banach modules once more. So as I told you, people in abstract Banach space theory, abstract functional analysis would say a Banach space is a vector space, so it has scalar multiplications. And first we studied the space, then we studied the dual space, then we studied all the operators, maybe all the operators from one Banach space to the other one. In harmonic analysis, we have seen we are interested not in all the operators, we are interested in the one which commute with translation. If we go to the Fourier transform side, these are operators commuting with multiplication. Then you have to sit down and verify, okay, if an operator commutes with multiplication, you can apply it to plateau function. So if some operator commutes with multiplication with plateau function, you find out locally it must be a multiplication operator. But if it's locally a multiplication operator, you glue the pieces together, you have a multiplication operator. You can also think in terms of a matrix. If somebody is giving you an operator which multiplies the coordinates x1, x2, unto xn, it must be a diagonal matrix, and the multiplying sequence are the entries of the diagonal matrix. So these are the subclasses that we have, and because we have seen LP spaces, other function spaces, let's mention that they are good examples. And the first algebra that comes to mind for discrete sequence space, it will be L infinity. For LP space, it will be capital L infinity. So you can say, maybe we mostly discuss the discrete case here, and you read this at home later on. If you want to know what are the sequences which multiply coordinate-wise, and then it's very easy to say, well, if you multiply with a bounded sequence, you can control the LP norm of the resulting product sequence by the size of the multiplier times the other one. Converse, is it true that if you have a sequence which multiplies LP into itself, that it has to be bounded? Well, first you say, okay, I look at the unit vectors. These unit vectors are all bounded in LP, for any LP. They have norm 1 in any LP norm. Then you apply the multiplier. What you get is just that unit vector multiplied with the entry at the place. If the unit vectors are bounded, all their multiplied versions, the image under this multiplication operator must be bounded. So what you multiply must be bounded. So it's very easy. The pointwise multiplier algebra of an LP space is just L infinity, and you can now formulate in an abstract way and say every little LP space from 1 to infinity is a pointwise Banach, is a Banach module over this Banach algebra. And L infinity allows conjugation as an involution. So it's even a C star algebra. It's commutative, and it has a unit element. Now, algebras with unit element plus commutative are more or less typically like this, except they can be on a measure space and so on. We don't want to discuss them so much because they don't help us too much to understand L1. L1 is some object where we do not have identity. Therefore, I think to understand better what's going on is to replace the L infinity space by C0, because that's the sequence space which is the closure of the finite linear combinations of unit vectors, which is more or less what we think is the same as the closure of the continuous function with compact support in the supremum norm sense. And also because I'm using this terminology, it's not completely standard. I mean, I think many people have picked up this terminology. I would like to mention that I call spaces, which in my viewpoint have an L infinity structure, are called solid spaces. So solid spaces, by definition, look slightly different. You're saying, I know the absolute value of a function in LP, and somebody is making some new function which is smaller coordinate-wise. So you have a function in LP, you have another sequence on the same index set, and it's point-wise in absolute terms smaller than, of course, LP norm of the space. This is an LP and has a norm which is not larger than this one. This is called solidity. Why is solidity useful? Because people in, let's say, wavelet theory or in application, they would say, okay, we have some signal, some image maybe. We have picked up the wavelet coefficients. There are many coefficients, but fortunately, we are getting a good compression. There are only relatively few big coefficients, and the small ones we throw away. So if somebody takes a sequence, replaces all the small coefficients by 0, that's called hard thresholding. Everything which is less than epsilon is put to 0. Then he's staying in the space and he's not increasing the LP norm or the mixed weighted LP-LQ norm. That's why these norms are so important. Secondly, people might say, no, it's unfair. I mean, if you're kind of very near the epsilon, if you're slightly below, you're thrown away. If you're slightly above, so maybe we should have some smooth transition so that, I don't know, from epsilon 1/2 to epsilon, you're more and more getting recognized, and then you are preserved or so. That's called soft thresholding. The other thing might say, well, I want to transmit information, the image you first get in your mobile device, a coarse version of the thing. I mean, you're doing a voice, and you want to have a conversation with somebody at a distant location with very low bandwidth. So the information is not allowing you to kind of show the person, but you might be able to have to transmit the voice plus a coarse version. Later on, you realize now there's more space and you can have more details, so it's good to know. Throw away the information that's not so necessary. Throw away the high frequencies, the fine details or so. So in this case, you would say, I do not decide on the, depending on the size of the coefficient, but on the location. If it's maybe in the break of a concert, you might not even record anything. You throw everything, put everything to 0. So when you play it back, you don't hear the noise in the room. Okay, that would be something. So the point is, you should not leave the space. And it's a very big thing a very big difference to have solid spaces compared to Fourier series expansion. That's something I also was looking up recently. Professor Temlyakov in South Carolina is an expert on this. You can say, well, what would be the classical situation? Classical situation is LP spaces, Fourier coefficients. L2, you start with L2 Plancherel, L2, you have this property, no problem. Then you go to LP. So P between 1 and 2 would be interesting. So you can ask, well, it's plausible. I mean, if you preserve the big coefficients and you throw away the small ones, then probably nothing can happen. But then he has constructed examples where by doing the truncation, the LP norm explodes. And the effect is based more or less, I mean, you have to really do many details or so. But why can LP norms be small? Actually, one has to look up whether it's P larger than 2 or maybe it's P larger than 2 and not smaller than 2. So maybe why can you have a function with a large norm in terms of Fourier coefficients with a low amplitude? Well, because these waves, these pure frequencies can up and cancel a lot. So if you are having a superposition of many frequencies which are made group-wise so that they cancel each other to get small contributions, but there is one just slightly above the threshold, the other negative below the threshold. Then you can make, by thresholding a kind of a nasty point for this very nasty constructed function, all the positive ones are surviving, and the negative one who would make the amplitude small, and therefore LP norms small, and LP norms for large P, I would guess, small, are lost, they are thrown away. And so you can say, well, I can have a sequence epsilon going to 0, and not only does the remainder, I mean, the remaining coefficients does not go to 0, it even explodes. So kind of, I think what you can do is to find the worst explosion rate for epsilon 1 over n, so that it explodes like, I don't know, some n to the gamma for positive gamma. And that's, of course, some situation that you would like to avoid. So that's why Fourier analysis and LP norm does not fit too well together, but in other, so Fourier algebra is clearly not having this property. You can have a function which is a nice bump function that you obtain by stretching. All these bump functions, if you dilate them, it's like on the Fourier transform compressing with area preserving. They have all equal Fourier algebra norm. And it's very plausible that if you have a very broad plateau function of norm 1, you can have an oscillating function below this, which is much bigger. So that's why you have these properties. So again, I would think for the discussion we will be mostly interested in those, and that's a kind of a summary in the Banach module terminology, because this was one of the questions. What are the spaces that we have, and what are the statements that summarize observations that we have already verified? We have the bounded measures. We have introduced the convolution through the multiplication or composition of operators. And we have even seen that for discrete measures, it's translation operators. Discrete measures can be are commutative, therefore the limits are commutative. It's enough to do it pointwise. So we have a commutative Banach algebra. Inside of this, that will be discussed in much detail next, is L1. We have C0, and if you want to understand things without measure theory, even without continuity, you take C0 as a first test case. What is happening? So one statement is in the Banach module theory. I don't know if I have written it up in the notes. You will find, and I repeat it in words, the concept of an essential Banach modules. Essential Banach modules, if your Banach algebra has approximate identities, are those where you're applying these approximate units and they work as if they were, they work as approximate units on the space. So you may remember in C0, the approximate units were those functions which are uniformly convergent to constant 1 over compact sets. Discrete version, or maybe my prototype is plateau functions. So if you think of the finite sets in the discrete setting or the compact sets in the plane, maybe I'm thinking of, I'm covering the whole plane with I don't know, balls or ellipses, which are getting bigger and bigger and bigger. Then of course you can imagine for every compact set I can find a plateau function. How are they directed? Now if you are saying I want to have this plateau and this plateau, of course I take the union. That is better. Then I have a larger plateau, larger than both of the original plateaus. And so the family of plateau function is a good approximate unit. Apply this to L1 or to LP. It's not written up. I was just probably saying you can do it with continuous variables. Then I would say little LP is an essential C0 module. It's just same finite sequences are dense in LP. And it's but only for here it's correct. Essential if p is less than 1. There's no hope to approximate constant 1 by functions which have finitely supported sequence because the error is always 1. So that's where really this weak star convergence comes in. As a side remark, what is weak star convergence in L infinity? Weak star convergence says, well, if I apply my sequence now in L infinity to an individual L1 function, I should see convergence. Well, if you apply the abstract concept of weak star convergence applied to the dual space L infinity, which is the dual of L1, it's necessary that for every L1 sequence it's okay. If it's good for every sequence, it must be good for every unit vector. So I'm sitting at coordinate number 50, and you give me this sequence of L infinity. I'm not interested in all the things that happen elsewhere. I'm looking if at my position, eventually I see convergence. So for example, we have larger and larger plateau functions. So you start to, maybe here's 0, you have a plateau function, and a larger plateau function, a larger plateau function. I'm observing at coordinate number 3 million or so. I have to wait a long time until you're stretching your plateau function, but eventually the plateau will be large enough to include my position or so. And from that point on, I would say it's okay. So it has stabilized. I'm getting 1, 1, 1, and the plateaus grow and grow. The guys further out have to wait longer. So it's really a necessary condition. On the other hand, if I say I observe convergence on single coordinates, it's clear that you have it on finitely many coordinates. If we are 300 coordinates, eventually we will all be covered by these plateau functions. If you have a general L1 function, we have up to some epsilon the same situation. So that's just a simple argument. So weak star convergence is a nice abstract concept, but it boils down to the convergence pointwise or coordinate-wise. And if you think of discrete setting, it means uniform convergence over compact sets in the index set, which means finite sets. Compact sets in the discrete setting are finite sets. So it's not big difference to what we have seen in C0. The next thing was take the bounded measures and look at them as C0 module. There are two ways. One was we were defining the product of a pointwise product of a measure with a function by moving it over. But we also had a little discussion, and I've written down carefully in the notes, that it's really the adjoint action. So if you have a dual space, you just do the action on your space. So mu times h is a new functional. If you apply it to f, it's you move the h over to the f, so it's mu applied to hf. So kind of, roughly speaking, memorize mu times h times f is meaningful a priori, because mu can be applied to h times f. Whenever h is multiplying my space, Banach space, into itself, I can multiply it and can do it. On the other hand, it's nice to have the symbol mu times h, and we have split our measure into mu times psi with this poo-poo into little pieces. We have seen that the sum of these pieces is everything in a nice norm-convergent way. But if I take a mu times finitely many psi I, they add up, we also have seen, they add up to a plateau function. So this mu times plateau function is approximating, in the norm sense, the mu. And that's why this is an essential Banach module. Now, the other thing was we have made a multiplication which is exactly turning. Essentially, we have said the operators arising as moving averages is a subalgebra of all the possible operators. It's exactly the ones, the closed subalgebra of all operators commuting with translation. Therefore, this module structure comes in. And now the next goal, so to say, will be to say, well, but we can view L1 as a closed ideal of this here. And then, of course, every module that allows the measure action will be an L1 module as well. And then the question of is it essential or not is more interesting, because if somebody tells you you have an essential, no, you have an abstract module over the bounded measures through convolution, that's I have to say. Maybe you can say later on we will see bounded measures convolved with LP goes into LP. And that's a really Banach module, and there's no problem. Is it essential? And then say, well, can I take the unit vector? Yes, the unit vector repeated as many times as you want is an approximate unit formally. So it's clearly, it acts, the unit delta 0 convolved with f, even in LP, is giving you the f. So every module over some element with Banach algebras with unit elements is fine, so that's not interesting. Okay, so we have seen in the introductory part that L1 can be introduced with measure theory. Lebesgue integration is a good way of, is exactly the right way to do it. And I tried to avoid L1 most of the time. So if you check the notes, I think I have not used it anywhere in a significant way. Just to tell you what I'm doing is not something completely different, but I'm doing it in a different way. In the lecture notes, in the full version, I'm really postponing it very far, even further. Why? Because I tried to see how far you can get without using the Haar measure. Now, here the course is, of course, not, I think it would be too abstract and not useful. One should say, well, we know what the Riemann integral is. I mean, that's even for undergraduate engineering students something they can use. So why should we avoid using the Riemann integral? It was actually motivating many of the things. So I could not explain this discretization procedure without explaining Riemann integral. So why trying to avoid integrals if I'm using as motivation for some basic step in the whole procedure? So, but kind of in an abstract situation, the question is, how can I do integration on a locally compact group? I just tell you what you have to study if you want to do it, if you do it in so to say, in a way which I would not find optimal. You would read some papers about, or in the book, some proofs about the existence of the Haar measure. The Haar measure, which is an invariant measure, which you can apply to test functions. And this is actually constructed by the way that, kind of going backwards from this definition that I gave. I was saying you have a linear functional on the test functions, but it's the same as having a measure. So they say, well, we want to do integration, therefore we have to produce a measure. But how do we get the measure? By defining a linear functional. So really what I think my reading is of the existing proofs of how to create the Haar measure, usually it's you prove existence and uniqueness more or less in one way, is to describe a linear functional on the space of test functions which has the property of being invariant. And if you look a little bit more closer, I really would say what you do is to have a coarse version of an integral which is not exactly additive, is not exactly translation invariant, but it's more or less like a Riemannian sum. And if you take all these almost linear, almost invariant things, they are a collection of linear functions which have a limit in the weak star sense, and that's perfectly additive and perfectly linear translation invariant, and then you have already a linear functional. So somehow, if you take the main part of this construction, then you really get a linear functional on the function of test functions, and that's what I would like to say. That's enough. You don't have then to go on to produce a measure on the sigma algebra that would allow you to make L1 and all these things. So it is enough to have some functional. For us, this functional is existing, and it's the Riemann integral. And so if somebody is giving me now a test function, a continuous function with compact support, because this is what I can do on every group, I would say integration against the test function via Riemann integral is the action. So every mapping, the input, the f I should write, is in C0. So for every C0 function, clearly f multiplied pointwise with k is a continuous function with compact support, which can be integrated without any deep Lebesgue integration theorem. Is it linear? Yes. Can you estimate the absolute value of this number, this potentially complex number? Yes. You put the absolute value to the inside, and you integrate, so to say, the positive version, and that's really no problem, and you can do it. So the interesting part is now, are we getting bounded measures, and how can we see, directly looking at the function, what this new measure that we produce, we will call it the measure induced by the function, or we call this mapping, which assigns for a test function a measure. I call it a natural embedding because it's really natural to do. And it's also actually commuting with all the things that we are interested in. You can say, well, what happens if I take the function and shift it first and then turn it into a measure, or I take it, make a measure, and then I move the measure? Is it the same? And then I would say, yes, that's like rational real numbers. If you add to a rational number 3/4, or you say, no, I'm adding 0.75, and you do it as a real number system with computations in the real numbers or the complex number, you get the same real number at the end. So it's really compatible. You can multiply k with a function. You can multiply the function first and then make it into a measure. That's why this definition is very meaningful that we have already. Or you can create the measure first and then multiply the measure. That's really, it's like a kind of associativity. Whatever operations you have, they have a meaning in the old world and they have a meaning in the new world, and now you can identify certain things, and as we will see, it's identifiable if you take the right norm. So I'm not sure if I have anything. No. I think I don't have to repeat it here. I just say it in words. What is the L1 norm of a function? Well, let's assume it's an imaginary, a real valued function. You look at the area between the graph and the function. So positive parts are taken positive, negative parts are taken positive as well. Or you take a complex valued function, make it positive, and take the integral over this. So that's the L1 norm. Again, the L1 norm is well defined. So you can ask yourself, what can we say about the continuous function with the L1 norm obtained through Riemann integrals? Answer is, it's a normed space. It's easily to see subadditive, the property of the norm. And then maybe a nice question is, how can you prove that the norm is 0, but that the function is 0 if the norm is 0? And then you say, well, if the function is non-zero, it must be non-zero at some point. Continuity, it cannot, let's say it has a value epsilon. Well, then on some interval it will be still larger than epsilon over 2. So you can put a little box below your graph, and that box will have height epsilon over 2, width like 2 or 1 delta or so. That's good enough to say it must be positive. So it's clear this is a nice space. Continuous functions have integral 0 even if and only if they are 0, and that's why you don't have to go with equivalence classes and these things. Okay, so we have a normed space, but it's not trivial. Okay, I think I did not write down in the full notes. You can see it is not very deep, to check that you can control the norm of this by the L1 norm. So essentially you're saying, well, absolute value of this is at most absolute value of this here. You put it in and you say, well, what do I know about my k? It's at most, in terms of absolute values, the sup norm. That's really the best norm that you can put. Pull it out. What is remaining is integral absolute value k of x dx. It's L1 norm. So this is quite easy. Now the other question is, how can you prove that it's equal? That's really something where I realized that there's quite a difference. I mean, you can spend quite some time on trying to find out what it is. What I guess is that you would probably try to do it first for non-negative functions on the real line, then maybe for real valued functions on the real line, then for complex valued functions on the real line, maybe then go to R2, see that it's not just left end and right end of the function, but it's two-dimensional or so. And so for something on an abstract, that was my wish to have a nice proof for in the setting of locally compact groups. And I will show you more or less a picture that tells you what you should do. So I couldn't rescale it better, so I have to stay with this. So what we have to try to do is to multiply our function. So I was choosing here a real valued function. Of course, I was using MATLAB to create a low-pass signal, making it real valued, and throwing away the imaginary part. So then I have a smooth function. But still, it's not clear, I mean, how to create the red function. I will try to tell you. That's really more or less the MATLAB analog of my proof idea that is in the lecture notes. But it's much better to describe it by pictures. So what do you see here? This green function is more or less +1 where the function is positive and -1 where it's negative. So the idea is very simple. Oh, he's taking the signum function. The signum function has maximum 1, and so it's +1 or -1, maybe 0 if you say it's 0 where you have 0. So that's very good. So if you would say, well, I have a measure, I would say I take the positive part, the measurable set where the function is positive part, or the open set where it's positive, the open set where it's negative. This is a measurable set, and you can do it. I'm not allowed to take a discontinuous function. Okay, then of course the idea was, well, I have to be careful at the zeros, so that's where the one-dimensional proof would be relatively easy. You say, well, this is a 0, we stay away a little bit, so we stop to do it, and we make a piecewise linear connection then down, which stops through the 0. Then on the other side, a little epsilon room, and that would not destroy the integral, so we get more or less absolute value of k of x, except a very small set of very small total lengths. That would be fine also. But then there was an extra problem. When you have a continuous function with compact support, that was giving me some trouble, and that's why I want to tell it to you. Continuous function with compact support, and they say it can be complex valued. So somehow you think, well, probably the phase will be also continuous. Answer is no. So now I'm trying to show you how I view such an example. This is my time axis, so my fingers are now pointing at time t. This is my value in the complex plane. So I have my blackboard in front of me, and if I go to the time axis, I will you should keep this in mind, because I cannot wrap my right hand around the left hand or so. But what I'm doing is maybe to the end of the table, that's where the function is dipping down to 0. So I have the time axis, a function which is going, and if you would have the absolute value, it would go down here. But the function would be something like this. So as you approach 0, the rotation is starting to be more and more nasty. So somehow I really have to try to keep something which is having more or less f divided k divided by absolute, absolute k divided by k. And I can write it where this is not 0, but near the zeros I have to throw everything away. So roughly speaking, I have to do the following, and that's the proof strategy. I have to find the set where the function is 0. Now there's an open set around it where this function is away from 0 by some small epsilon. On that set I can take the phase function, absolute k divided by k. This is a function which is good, and that one has to be continued. And if I then put, this is my f now, because the absolute value was never between outside of 0 plus 1. This is also a function which is compactly supported because it's living where the original function is living, actually inside. And it's exploring most of the things. And I only have to make sure, and that's I leave out these things, that the 0 set cannot be so bad that these fabricated functions is not fine. So I have more or less k divided by k, k absolute divided by k. If I multiply it with k, that cancels out, and I would get k. Well, almost everywhere except the trouble points, but they are a small set, and therefore everything is fine, and I can do it. So the point is, I'm not thinking in terms of measure theory. That's another important point. I'm just saying I'm splitting the function into two pieces, or it's acting in two pieces. And at the places where I'm doing this trick and throwing away information, where because of the high oscillation or so, the function is already near the 0, and it will be small anyway. So and whatever pieces I've thrown away, which might give trouble, applying a functional to apply to a function where the supernorm is small is no problem. So it's again this splitting, main part small and small remainder, but now not compact set and infinity, but trouble set is small set, and main part is where most of the integral comes from. Okay, so in this way we have the situation that we can embed via Riemannian sums the test functions into the bounded measures. And now we are in a very convenient situation, because we can say we are living in a dual space. And as Professor Kulkarni was explaining it, the dual space is always complete. Therefore, if we take the closure in the measures, so we take all the measures which are approximated by regular measures coming from test functions, then we have a correct copy. And because Lebesgue theory tells us that L1 is a Banach space containing the test functions with compact support is a dense subset, and because of the uniqueness of completions, if you have two completions which are built in a different way, in this case I have embedded my normed space isometrically and closed up in a Banach space. That's one way of getting a Banach space containing the original space as a dense subspace, and the L1 space is another, and another abstract completion is maybe the third one. They have to be all isomorphic. So essentially, of course, what you do, if I want to do something here, I restrict my thing to the dense subset, where I can identify clearly. I mean, it's an ordinary function, a measure coming from an ordinary function, and that's all. So this only raises the question, and that's maybe what I will do next, and then we have a break, is what are the measures that we get in this way? The traditional way of looking at this is these are exactly the absolutely continuous measures. So the absolutely continuous measures, and I don't know how much you had this in your analysis courses, I must say it was one of the fascinating topics in our first year of analysis, which was a tough thing, is where we learned, of course, epsilon delta for continuity, epsilon delta for equicontinuity, uniform continuity, sorry. So epsilon delta for continuity means if you tell me where you test it, I can I should be able to find for a given epsilon a delta. Uniform continuity, you don't tell me where you test it, and I will have to find a delta where you can choose afterwards the point which you think is the worst for me, and my delta has still to be okay there. Absolute continuity is essentially to make it even worse. It says, well, I should be allowed to test on many different places and add up all the troublemakers, so to say. The only restriction that I have when I do the test, you give me an epsilon, I have to find a delta. And I have to choose this delta so that you can collect many, many trouble points, countably many intervals which are disjoint, take the difference between the maximum and the minimum value, so to say, as long as the total length of these intervals is less than less than delta, sorry, then the amplitude should differ, again summed up over everything, should not be more than delta, epsilon. Yeah. Yeah. So essentially, you can imagine if you shrink, this has to do that you know, well, if a set can be covered by a union of intervals of total length epsilon, for every epsilon, it will be a set of measure 0. And in the Lebesgue sense, so this is the kind of modern. Then the established concept is saying measure. Now, if sigma algebra of Borel measures, and you have the sigma algebra of Lebesgue measurable sets, a set is of measure 0 in the Lebesgue sense, then it has to be also a set of measure 0 in this sense. So you would say, well, if somebody is giving me a Lebesgue integrable function, you integrate over a set of measure 0, clearly the resulting product is my L1 function, which provides the density, times a function which is 0 almost everywhere. So integrating something over a set which is only non-zero in the set of measure 0 is, of course, clearly a measure which is having this property. The converse is not so obvious, because you say, I have a measure abstractly defined on such a sigma algebra, and if it's a set of measure 0 in the Lebesgue sense, it has to be a set of measure 0 in that new measure sense, that it must have a density, and that density is in L1 in the Lebesgue sense. That's needing some work. That's a radon nicotine, more or less. I was learning about this concept, and that's really the classic view that you can find, for example, in the book of Nathanson. In the following way, you're asking more or less the question, one is the very basic principle of analysis, that taking derivatives and taking the inverse, the running integral, where is this, are these inverse operations? And the first thing is, of course, you take a step function and say, okay, it's differentiable everywhere, it's constant 0 here. Well, there's just one point, constant 0 here, anywhere. So a jump function has derivative pointwise classical sense almost everywhere. If you take the antiderivative, 0 is giving you 0, nothing. So clearly it's not even continuous, so it's no chance. And I think I found it a very nice proof that was contributing to my fascination for analysis or so, to say, well, if you have a function with this property, with this total length of epsilon, that it has a classical derivative almost everywhere, and you get a function which is well defined, so you prove it's an L1 function. And L1 function can be integrated from minus infinity to x, so antiderivative is meaningful, and is giving you back the function. So if you're asking, when in the classical sense is a function absolutely continuous in that sense of bounded variation, then you have this property. Now, it's very little known, but I like to popularize it. There was a paper, I think 29, by Mr. Plessner, who was at the time when this concept of absolute continuity was established, and there was also another concept about bounded variation, which is modern terminology of measure theory. So non-negative real valued measure would be something which is going up, that's a positive measure, or going up and down and up and down, and if the total of all the ups and all the downs is finite, you would say it's a bounded measure in the modern sense, and that's exactly the thing. So it was well known that every absolutely continuous measure is of bounded variation. We say every L1 function is a bounded measure. So in that sense, we are very close to this situation, but in a very different description. And Mr. Plessner was proving that if you have a function which is of bounded variation, so you have a a notion of what the norm is of this up and down function. But if you shift it, and if the shift is depending continuously on the position, so if you shift a little, and then you take the total variation of this, then it's absolutely continuous in the classical sense. And then when I found this result, I said, oh, that's what we know. L1 is exactly the subspace of all the measures which have continuous shift. So that's, so to say, the last part of what I want to do before the break is how can we characterize this set of absolutely continuous measures as a set of measures, or now in our context. I don't want to talk about measures, sets of measure series, but I can, of course, write, I have a measure, I convolve it with a Dirac delta if you want, then I have the shifted versions. This is, of course, the measure norm, and are there measures which are going to 0? I must say I'm really looking now for an argument. Let's assume you don't have Haar integral, you don't have this embedding as we have it in the Euclidean set, but if you have just a group, I am not yet able to prove that there exists any measure having this property. That's, yeah, just maybe the trick is I would need the Haar measure to do it, but I think somehow I would be happy to avoid it. It should be enough to have some approximation, or cheap approximation of the Haar measure. But yeah, okay, that's just a challenge, so to say. But of course, what we know is if it's an embedded measure, then the shifted measure of a regular measure is, of course, the measure coming from the shifted function. Everything is linear, so we're saying, well, if you give me a test function, then the L1 norm of the test function minus shifted is going to 0. So every embedded function is in this class. Another exercise is, can we show that this is a closed subspace? Now, in the norm sense, closed in the norm sense, answer is yes. That was one of the reasons why I was suggesting, let's look at the bounded uniformly continuous functions. They are the set of functions in the bounded continuous functions which are having continuous shift. And to show that they are closed because they are described by this property with the sup norm was a preparation. Yeah, CS is just my private notation for continuous shift. So it's not compact support, but it's yeah, it's a bit but it's just. We will not use it for a long time because, of course, the next point is we show that this is L1 in the usual sense. But a priori, we have now 3 layers. We have the set of embedded functions, which are not yet complete. But if we take the closure, we can call it L1. We will see it's justified. A priori, it's then the closure of the set of with continuous shift, and then we have all of the measures. Remember, in this space of continuous bounded functions as the big space, we would say we have C0, we have CUB, the uniformly continuous bounded functions, like a sinus function is not decaying, but it's still uniform continuous, of course. And then we have all of them, including the bounded and not uniformly continuous functions, sequence of triangular functions. Okay, but what is the situation here? Okay, so it's also a closed ideal. Of course, this is again because if somebody convolves such a thing, so if you have Tx mu1 with mu2, you can pull out the Tx, and you can again say a convolution product can be shifted by just shifting one of the factors. Remember, Tx is just the convolution with delta x. So to say delta x, associativity of convolution that we can use, delta x multiplied or convolved with mu1 with mu2 is the same as associativity delta x with mu1 bracket and then put together. So associativity tells us we can pull out one factor, therefore this is clearly an ideal in the bounded measures and so on. But we have another, this is more or less I think saying what I have said already. Yeah, okay, there's one remark that I have to not develop too much, otherwise we are spending too much time or so, is we have already seen that we can convolve, that's kind of the definition, we can convolve measures with functions. That was our original idea, that if somebody is giving a measure, I called it the convolution operator C sub mu acting on the function. And we were starting to write star for it. And the associativity is really because we're making the star within the measures such that even if you take it first inside the algebra and then act it, it's really associative. So that's why this Banach module terminology comes in. But now we have another problem. Because there's so much duality going on, we have an action of measures on C0. Therefore, there's an adjoint action on the dual of C0. Just think about this. So now we have two convolutions. The original convolution within M, the measures, and the action of the measures on C0, and the adjoint actions on the dual of C0, which happens to be M. And we can be confused, or we can say, well, we have learned that if you understand everything on the discrete measures, you know what's going on, because the rest is taking limits. So you have to try to see what happens for Dirac's, and that I just mentioned you. So the joint action is just convolving with the flipped operator. So you test it by saying, well, what happens, the action of a delta as an operator on the functions? It's a shift operator. What happens on the measures, and what is the joint action? The joint action of a delta should be, I mean, you have a new version of the star. On the f is just taking f and then you apply it to the function. So what is mu applied to a shifted function? And you will say, okay, we have learned that you should have a minus here. So mu, the joint action of a delta is the convolution with a negative delta. So we just have a flip. And that's where this flip comes in very handy. I mean, such a very simple observation. The flip is, of course, isometric in the C0 space, in the bounded even. We have put it as a flip on the functionals. And suddenly, within the operator somehow, if something is a moving average, the moving average with the flipped version is, of course, also having the same norm. It's no problem to flip it. And suddenly, we can say that every operator is actually the adjoint of something which is understood. And then I leave it out to you to say, for the deltas it's OK, for the discrete measures it's OK, and by limitation you find out we don't have to worry. There have been, abstractly speaking, two different convolutions, the adjoint action of the action on C0 and the internal, but they're the same. And that's why from now on we will write star, associativity will be granted as long as we have an interpretation of within one of the contexts. It's not a good idea to say what people can do, and I have put some reference into the thing, that you can look at the problem individually. You can find three distributions where it's possible to define both versions of the associative law, so you make brackets. In some way you define a product very not artificially, but very kind of technically, and say in this situation we can do it, in this situation we can do it, and it turns out you get two different distributions which are not equal. But it's far away from this situation. So this kind of when you're going into a risky environment and you're not following the instructions, you should be warned that there can something can happen or so. But it's not. Okay, now to come.
MCS, you are taking the norm from M of RD only. No?
Yeah, yeah. So I have corrected it already, but not in this slide.
Okay.
And now the last thing I want to do, and 3 or 5 minutes I hope I can do it, is to show that L1 is actually the same as the continuous shifting measures. So the idea is really very simple. What you have to do is you have to convolve the measure with this compressed Gauss function. So you take a Dirac sequence and apply your measure to the Dirac sequence. And now this complicated discussion that I had, and you can forget about all the details, can be put to use. I can choose whether I'm saying, you give me a Dirac sequence, and this is a sequence of measures. They happen to be continuous shifting, and they are regular measures, and they are induced by the Gauss family. And I'm doing within my algebra, I'm doing computation. If I do it in this way, I'm saying the measure is in the measure algebra, the convolved measure is in the measure algebra. I can check whether the norm is shift invariant. Well, we have already seen this is a closed ideal. the regular one, the guy with the Gauss function, is having continuous shift. So I'm approximating and multiplied with whatever it is in the algebra, it's okay. But then I can also switch the view, and I can say, no, I'm convolving a measure with a nice test function in C0. Therefore, I can apply it. And what I'm getting is, this Gauss function is in C0, I will stay in C0. And then somebody says, more or less, I have a bounded measure which is coming from a continuous function, so maybe it's integrable in the Riemannian sense, and that I'll leave out a little bit of detail because of the tails. I mean, so I think in the proof that I wrote down for this course, I wrote down that first I think of the Gauss function, but then I replace it by maybe this bump function that we had in the practical part of the course. So some nice bump function compactly supported. And when you want to know whether the measure can be approximated, we have seen that it's enough to approximate it if the measure is compact support. The rest is again epsilon or so. So roughly speaking, I have tried to boil down everything. Regularize a measure of compact support with a function of area 1, non-negative, and let that shrink. In the interpretation of applying a measure to a function, it's a continuous function. And then the other thing is it convolving in, yeah, that's maybe another point. Is it approximating the measure in the weak star sense? Because I cannot expect that something which is closed in L1 in the measures can have arbitrary elements in the limit. I mean, Dirac is certainly not in the limit of L1. So what I have to do, just in looking up, this is a typo here, ST rho with G. What does it mean? It's the joint action, so actually I should write ST rho G flipped, but I think the bump function can be chosen, and I take a symmetric one. So I have to apply this, but we know, and that's what you really have done in the beginning. If you take something like a bump function, it can be the Gauss function, but it can be also a cubic spliner. So it will converge, this part will be convergent in the subnorm to the limit. If you apply a linear functional, which is continuous, that will be also convergent. So somehow, well, if somebody is giving you a nasty measure, can be a discrete measure, some diffuse measure, so you can smooth it. And one interpretation is telling you, I'm getting a continuous function, and therefore I'm getting a regular distribution. And the other thing is telling it's a weak star density. And that's more or less what I wanted to say, because now with the different interpretation, and you see here I'm having things like ST rho G. You can choose if you look at this as a function or as a measure coming from this. This has to be justified, but I think once one has explained that it can be easily justified, you can later concentrate on these transitions. And so from now on, we can say we have seen if it's continuous shift, and the main point is what is the difference to C0, CUB, and CB? Measures are always decaying at infinity, even if they're very abstract, because of this little piece is summing up. And so we can say if a function has continuous shift and decaying at infinity, it can be approximated by test function. And in CUB, it is just C0, and that's a different space. I will check, but I think that's more or less everything. Yeah, so I think that can be left as a statement at the very end. We have seen that the closure of all the measures within the bounded measures of all the test functions, or of the regular measures, they're the elements with continuous shift or a closed ideal. All these Gauss functions or compressed Dirac measures, or just even shrinking families of whatever function you have of area 1, they can change the shape even, will be Dirac sequences, so they will bound it and act as approximate units. I'm not sure if we have done this in detail, but it's clear if you have a continuous function with compact support, it will be uniformly approximated, and therefore you can approximate an L1 norm, and the rest is taking care about details. So we will work with this Banach algebra in great detail. And I think, yeah, that's actually the end of my slides, and I'm sorry for going a little bit over time or much over time. Thank you for now, and we take a break, and I will continue. Thank you.